Hi, my name is Shashank Singh Kumar, and this is my video lab report for Physics 2211 Lab 4 Oscillations. The purpose of this experiment is to compare the motion observed in real time and the motion modeled by the GlowScript code of the mass in both x and y directions, and to plot the changes in energy, that is kinetic energy, gravitational potential energy, spring potential energy, and total energy, calculated in the model. The methodology is as follows. The video provided was imported into Tracker and its motion analyzed. The x and y values were extracted from Tracker and exported as a CSV file. The GlowScript code was edited, and finally the output was studied. Concepts and formulas of significance. Newton's second law is a significant idea which can be expressed by the following formula. F net is equal to delta P by delta T. Newton's second law of gravitation is a significant idea which can be expressed by the following formula. Gravitational force Fg is equal to g into mass of the earth into mass of the mass divided by r squared into r hat. The conservation of energy, which states that energy can neither be created nor destroyed, it can only be transferred from one form to another, and the principle of energy are also important here, which can be deducted by categorizing the systems and surroundings in the experiment. The system consists of the spring and the earth, whereas the surroundings consist of nothing. The change in energy is equal to Q, that is heat, plus work done on the surroundings, is the energy principle. Another important formula for energy is delta E is equal to the change in kinetic energy plus the change in gravitational energy plus the change in spring potential energy, and the total change in energy is always equal to 0. The following are energy formulas also required for the experiment, such as the formula for potential energy, kinetic energy, spring potential energy, and spring force. The following video is the analysis of the motion of the spring using Tracker. System properties, initial conditions, and data for the coding of the computational model. The mass of the ball.m, has been set as 0.402. Ball.pos, that is the position of the ball, has been set as vector minus 0.123, minus 0.634, 0 as the initial position of the ball. The spring constant was calculated to be 0.7597 and L naught was found to be 0.648. The vector L was given the formula of L is equal to the position of the ball minus the position of the spring, and L hat was L divided by the magnitude of L as the unit vector. S was equated to magnitude of L minus L naught. The formulas for the energies from the previous slide have been used in the lines 94 to 97 in order to create the formulas for energy in the GlowScript code. The calculation loop for the coding of the computational model. The energies calculated in the previous section have now been set as the initial energies in lines 109 to 112. F grav has been set as the vector 0, minus mass of the ball into g, 0. F spring has been set as minus spring constant into s into L hat. F net is equal to F grav plus F spring. The velocity of the ball has been set as ball.well plus F net by ball.m into delta t. The position of the ball has been set as ball pos plus ball well into delta t. The updated spring values such as L have been set now as L is equal to the position of the ball minus position of the spring. L hat is L by magnitude of L, and S is equal to magnitude of L minus L naught. Once again, the new kinetic energy, the new gravitational potential energy, the new spring potential energy, and the new total energy have been calculated, and the change of them have been calculated as delta K, delta U of G, delta U of S, and delta E by subtracting the new energies and the initial energies. The following is the output from the GlowScript. The first graph is that of the motion of the mass attached to the springs. The second is the graph of change in energy versus time. As you can see, the change in total energy is 0. The graph of x-axis versus time is also given, and the graph of y-axis versus time is also provided. In the graph of the x-axis versus time and the graph of the y-axis versus time, the red line represents the experiment and the blue line represents the model, whereas the graph of change in energy versus time, the red line represents delta U graph, the green line represents delta U spring, the yellow line represents delta E, and the blue line represents delta K. Answering the what does it mean questions. What does it mean? For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. Yes, the energy system is justified as the total change in energy is always equal to 0. As you can see in the graph, the delta E line is a straight line across the x-axis, which is y is equal to 0. Hence, the change in energy is equal to 0. What does it mean? Using the data you obtained in Tracker, make two separate estimates of oscillation periods. First by estimating the period of oscillation from the X position data, and the second by estimating the period of oscillation from the Y position data. Compare the two estimates and discuss. So I took the time period of 5 oscillations and then divided them by 5 in order to get the average time period for one oscillation. I did this for the X position and the Y position. For the X position, the time period was 1.7474 seconds, and the time period for the Y position was 1.6144 seconds. The time period for the Y position is lesser than that of the time position for the X position. This is most probably due to a greater number of forces working on the Y position compared to the X position. Thank you so much for watching, and I hope this presentation was useful.